Okay. Section 4.4 is fun, but it is complicated. This is business applications. So we're going to walk through like six-ish examples of minimizing inventory costs or maximizing revenue. Um, and so just bear with me as we go through these kind of step by step. So we have a furniture dealer who sells 500 desks per year. The desks take up floor space and warehouse space. The dealer estimates that his storage costs $6 per desk. The distributor charges the dealer a $60 fee for each order. So how many times per year and in what lot size should the dealer order to minimize inventory costs? So you want to sort of, you have this balancing act between what's on your floor in your warehouse space, um, or what's on your floor, like ready for customers, and what's in a warehouse somewhere, and how often these things get delivered to you. Um, so what costs do we need to consider? Well, the cost per desk for storing it, but also the cost per delivery, right? Because you don't want to deliver every time somebody needs a desk if it's going to cost $60 per delivery, no matter how many are in it. So our inventory costs here would be equal to storage costs plus the ordering or delivering. So in an ideal scenario, we would know how many are sold. And it happens linearly. So basically, here's the sort of the pattern that we're going to use for doing these. If X is the number of units in an order, how do we determine inventory costs? So we're going to call inventory costs C of X. This is going to be your storage costs plus your ordering costs. So storage costs here were $6 per desk. And then plus $60 per delivery. So this is the number of desks in storage. And this is the number of orders. So those are not both some variable X, but they're related to X. So we're going to call this one in general X over 2, assuming that we have about half of our inventory in storage and half of it on the floor. This is the average number of items. And then 500 is the total number of desks they're going to sell divided by X. That will give us, it's going to divide this into X desks. So this would give us the number of deliveries. This gives the number of orders. So 500 divided by the number of desks we're going to sell would give us the number of orders that we need. So we have the number of desks we're going to sell. This is what we want. Ideally, we know how many we're going to sell. It's X desks. So at any time, we should have half of those in storage, maybe, and half on the floor. And then the second thing, 500 divided by X, we have these 500 desks. We're going to split them up into X deliveries. So this would give us the number of orders. Okay, so determine the number of orders in the lot size. Size is our value X in order to minimize inventory costs. Okay, so we're going to find the lot size first. And then the number of orders. So going back up to our function c of x, I'm going to simplify this to just 3 times x. And then 60 times 500 is 30,000 times x to the negative 1. Okay, so I'm minimizing costs, so I need to take a derivative. So c prime of x here would be 3 minus 30,000 times x to the negative 2. And then I'm going to find a critical value because I'm looking for a min or a max. So 0 equals 3 minus 30,000 x to the negative 2. So we have here, if I add that to both sides, this is what we have. So I have 30,000 equals 3x squared. So 10,000 equals x squared. So x is plus or minus 100. Negative 100 doesn't make sense because this is the number of desks. So we're going with 100. So that's the point. The lot size is 100, meaning that 500 divided by x, which is 500 divided by 100 is 5. 5 orders would minimize inventory costs. And let's check that just to make sure. So I'm going to do the second derivative test. So c double prime of x would be positive 60,000 x to the negative 3. If I plugged in 100 there, it would be positive. That's 100 would be positive. So up like a cup. So we would have a local min. So the lot size is 100 and 5 orders of minimized inventory cost. That answers the question. This is C of 100, which is $600. So their minimum inventory cost is $600 for when they have 100, when they put their lot size at 100 for these desks. Okay. Here's another one. We have a hardware store that sells 96 chainsaws per year. It costs $5 to store a chainsaw for the year. There's a fixed reordering cost of $15. Find the lot size and the number of orders that will minimize inventory costs. So C of X here, it is $5 to store it for a year. So $5, and we're going to assume that we are, again, storing about half of our lot size at a time. And then there's a fixed cost of $15 for reordering. This is 96 divided by X. X is going to be our lot size. So we are trying to minimize 4X. So I'm going to simplify this. 50, no, that's just a 5x over 2 plus 1440 over x. So c prime of x is 5 halves minus 1440 x to the negative 2. So it's undefined at x equals 0. And then we want to know where it actually equals 0. So we have 0 equals 5 halves minus 1440 x to the negative 2. That's 1440 over x squared equals 5 halves. So 5x squared, I'm cross multiplying here, equals 2880. So x squared is 576 apparently, which means that x is plus or minus 24. Negative 24 doesn't make sense. So we are going to choose a lot size of 24. Means 96 divided by x, which is 96 divided by 4, which is divided by 24, sorry, which is 4 orders. We'll minimize inventory costs. And then you want to just make sure, check that that is actually a min. So C double prime. Negative positive 2880 x to the negative 3. If you plug in positive 24, this can be positive, which means up like a cup, which means it's a local min. So that's good. The actual minimum inventory cost is C of 24, which in this case is, I think, 120. So you have 24, 120 is your local min. Okay. Now we have store expects to sell 120 pairs of batting gloves during the next year. It costs $255 to store 1 pair for 1 year. To reorder, there's a fixed cost of $17 plus $1.60 per each pair of gloves. And what lot size and how many times per year should an order be placed to minimize inventory costs? Okay, so we have a similar situation going on here. It's $255 for the storage, and we're going to hope about half of the lot is in storage at a time. We have this fixed cost per order of $17. So 120 divided by X, that'll give us the number of orders, and then 17 times that'll give us that cost, plus $1.60 for each pair of gloves. So $1.60 times 120 pairs of gloves. So that is our cost function. So we have, if we simplify here, this 1.275 x plus 2040 over x plus 192. So C prime of x is 1.275 minus 2040 x to the negative 2. Undivided x equals 0. Set the thing equal to 0. So we have 1.275 equals 2040 over x squared. So you're looking at 2040 equals 1.275 x squared. Divide, you get 1600 equals x squared. So x is plus or minus 40. Again, negative 40 doesn't make any sense. So you're going to go with positive 40. The lot size is 40. So 120 divided by x, which is 120 over 40, which is 3. Orders minimize the inventory cost. Okay, And then we want to just check and make sure it's actually a minimum. So F double prime, or C double prime, I mean, would be 4080 x to the negative 3. C double prime of 3 would be positive. So concave up like a cup. So it's a local min. So that says lot. So the minimum inventory cost is C of 40, which is 294. We have a local min at 4294. Okay. Let's do, I'm going to skip this one. This is really similar to the one we just did. If you would like to see that worked out, just let me know. But I want to work through maximizing a revenue problem. So a discount store sells 84 radios per month at $20 each. The owners estimate that for each $1 increase in price, they will sell 3 fewer radios per month. How much should they charge for the radios to make their revenue? Okay, so we need a revenue function. How do we get that from the information? So revenue is going to equal price times the number of sales. So if they raise the price J times, the price is going to be $20 plus 1 times J, and the number of sales would be equal to 84, which is what they normally sell at $20 a month. But if we're increasing and they're going to sell 3 fewer radios per $1 increase, so it would be minus 3 times J. So our revenue function, R of X, or J, my bad. I don't know why I went with J, but whatever. Okay. Our revenue function, R of J, is going to be 20 plus J times 84 minus 3J. So again, that's the price, and this is the number of radios that are sold. So if they don't raise the price at all, right, this guy is 0, and this guy would be 0, and that is what they're doing now. It's 20 radios at, or 84 radios at $20 a month. Okay, so let's go ahead and keep working this out. We're going to FOIL. So we would have 1680 minus 60J plus 84J minus 3J squared. Combining those middle two terms, we get 1680 plus 24J minus 3J squared. This is a parabola, and that negative means it opens down, just like this. So it does have a maximum, which is good because we're trying to maximize revenue. Okay. I don't have space to do any more of this work. Let's use blue and come over here. This is RJ. We're going to do R prime, which would be 24 minus 6J. Set this equal to 0. We're looking for that maximum. So 6J equals 24. J equals 4. So they should increase. This is 4 $1 increases in price to maximize revenue. So they should charge $24 per radio. Let's see what their maximum revenue would be if they did that. Also, R double prime of J is -6. So R double prime of 24, 4 is going to be negative. So this is concave down like a frown, which means we would have our maximum that we're looking for. But R of 4 is equal to 1728. So we have a max revenue of 1728 at $24 per radio. Okay. Let's do these last two. A farmer estimates that if he plants 30 grapefruit trees per acre, the average yield per tree, that should be P, per tree will be 480 pounds. For each additional tree planted per acre, the yield per tree will be reduced by 12 pounds. How many trees should be planted per year to maximize the yield? So we're looking at the yield. Yield is going to be number of pounds per tree times the number of trees. So the yield, or the number of pounds per tree, is going to be 480 minus the yield per tree will be reduced by 12 pounds for each one tree planted. So the yield would be decreased by 12 pounds per tree. So 12x. And then the number of trees is going to be 30 plus x. If he plants 30, this is what happens. If he plants one more, this is what happens. For each increase by 1, this is what happens. So here's your yield. X is the number of additional trees. Okay, so the yield, if we FOIL that, you get 14,400 plus 480x minus 360x minus 12x squared. Combine like terms, you get 14,400 plus 120x minus 12x squared. And we want to know where this is equal to. No, we want to take a derivative first. Y prime would be 120 minus 24x. Set that equal to 0. So 24x equals 120 divided by 24. We have that x equals 5. So we maximize the yield at an increase of 5. So at 35 trees per acre. If we check this, y double prime is -24, which is always less than 0. So this is going to be a maximum. So an increase by 5 gives us, go back here to this and figure out what y of, this is y of x, whatever. Go figure out what the, what happens when you plug in 5. You get 14,700. So the maximum yield should be a IE, is 14,700 pounds from 35 trees. All right. And last one, we have a sporting goods store that sells 200 baseball gloves per month at $36 each. The owner estimates for each $2 increase in price, he will sell 5 fewer gloves. Find the price that will maximize the revenue. Again, we need to know what the revenue function. So in this case, revenue is going to be the price per glove and then the number of gloves sold. Okay, so the price per glove is going to be $36 plus 2 times X. This is for each. This is for one $2 increase. And then the number sold is going to be 200 minus 5 times X. Okay, so we're looking at R of X is 36 plus 2X times 200 minus 5X. Foil, we get 7,200 minus 180X plus 400X minus 10X squared. So 7,200 plus 220X minus 10X squared. Okay, so there's our derivative. We're going to find, there's our function. We're going to find the derivative now because we're trying to maximize the thing. So R prime would be 220 minus 20X. Set that equal to 0. So X is 11. So we maximize revenue with 11 $2 increases in price. So we have 36 plus 2 times 11, which is $58. Goodness. They'll sell 200 minus 5 times 11, which is 145 gloves at $58 each. So their revenue, max revenue, would be 58 times 145, which is $812. Okay, so this is kind of strange. Again, looking at this is a downward facing parabola, so it does have a maximum, so we're at least on the right track with that. And then we found that where that maximum happens and then what that maximum is. So yeah, that is 4.4. Let me know if you guys have any questions. Thank you.